So now let's find the solutions of sine equations. To develop a method to determine all of the solutions of a sine equation, like we did with the cosine equation, we are going to look at an example and use the unit circle to help. The first one says to solve exactly, sine of theta equals root 3 over 2. So if you've got this memorized, great. You may be able to just tell me that theta is equal to pi over 3 and that theta is also equal to 2 pi over 3. I'm going to just make sure that I did that right by looking at my unit circle, and sure enough I see square root of 3 over 2 at pi over 3. I also see it at 2 pi over 3. Now, is that a good answer? Well, almost, and I'm going to say almost because there is no limitation on theta. In other words, it's not just pi over 3, but it could be pi over 3 plus 2 pi plus another 2 pi. I could just keep going around and around, positive or negative. So I need to remember on both of my answers that I need to put a plus 2 pi k on both of them, and I'm being a little bit lazy by writing it like this, but you get the idea. All right, let's go to the next one. Solve exactly, and I'm going to go ahead and clear my screen so you can see what's on there. Solve exactly, sine of theta equals 1/2. So let's see, where is the sine 1/2? It looks like that's happening right here at pi over 6, and it's happening right here at 5 pi over 6. There's no limitation for my angle, so I'm going to say that theta is equal to pi over 6, and I'm not going to forget about the plus 2 pi k, and I'm also going to say that theta is 5 pi over 6 plus 2 pi k, where k is an integer. Now, one thing to note that you might be thinking about is, why do I keep using pi over 6? Or why do I keep using pi over 3? Why not use degree measures? And the answer is that I absolutely could do that. There's nothing to indicate to me whether my theta is in radians or degrees. So instead of putting pi over 6, I could have put 30 degrees. Of course, if I do that, then the 2 pi has to change to 360 k. 5 pi over 6 would turn into 150 degrees, and 2 pi would have to turn into 360. I think I've got one more example for you. Solve and round to 2 decimal places. Sine of theta is equal to 0.2, and in this case I know that my theta is in degrees, and not only that, but it's not all of the degrees. It's only the degrees located between 0 and 360. So I'm going to just go ahead and show my work here. I'm going to take sine inverse of each side. And let's see here, sine inverse of 0.2. The inverse and the sine cancel out. And my calculator tells me when I put it in, now make sure that you're in degrees, I get 11.54 degrees. So that looks pretty good. Let me just think about this one for a second. Sometimes when I get an answer like that, I just like to make sure that it makes sense on my picture. Remember what this is saying. This is saying that an angle that's around 11 degrees is going to produce an output of 0.2. Well, remember that when I had a 30-degree angle, I had an output of 1/2 or 0.5. So I think that maybe that angle would be about right here. Right? That height looks like it would be around 0.2. Now, what that does is it tells me, or it convinces me, that there is another answer. And where can I expect that answer to be? Well, when you have a positive sine value, then you have to have an angle that's in the first or the second quadrant. So unlike the cosine function where I was in quadrant 1 and 4, in this one I'm going to be looking for that same positive sine value, and I will find it over in the second quadrant. So how do I get that angle? For cosine, I took 2 pi, went all the way around, and then I backed out the calculator. I don't think that's going to work in this case. In this case, I'm going to go all the way around, but I'm going to stop at pi, and then I'm going to back out the angle. So pi minus my 11.54 degrees is equal to how much? Well, it's around 180 degrees minus 11.54 degrees. I get 168.46 degrees as my answer. And those two are my final answers because of the limitation on theta. I don't have to worry about multiples of 2 pi or 360 degrees K. So in general, trigonometric equations may have infinite solutions. Therefore, the domain of the function must be considered when you are solving. To find all possible solutions of a sine equation with a period of 2 pi, recall that the sine of theta is equal to the sine of theta plus multiples of 2 pi or multiples of 360 degrees, where k is an integer. Also note that theta is the angle produced by the calculator and that additional angles can be found by using pi minus whatever the calculator gives you. Of course, the only time that we really need to think about that is for angles that we don't have memorized. For angles that we do have memorized, we saw this one earlier with cosine, we should be able to just use our knowledge of the unit circle. So sine of theta equals root 2 over 2, and I am on the domain of 0 to 360 degrees. So think about this for a second. Where's the sign positive? That's in quadrant 1 and 2. And we know we have outputs of root 2 over 2 for multiples of pi over 4 or multiples of 45 degrees. So I'm going to say that my solution for theta is 45 degrees. And what would the other one be? 135 degrees. And just those solutions within the theta values of 0 to 360. Now for the second one, sine of theta equals root 2 over 2, there's no limitation. So I could actually say that my theta, I could write it in degrees or I could write it in radians. I'm going to go ahead and just keep with the degrees and say that theta is equal to 45 degrees plus 360 degrees K. Theta is also equal to 135 degrees plus multiples of 360 degrees, where K is an integer. Now I could have done that fancy Z, but I can also write it out if I prefer.